want to talk about one of my favorite objects in the world, and that's the Mandelbrot set. Perhaps one of the most famous sets or famous images in modern mathematics. I mean, this is one of the few objects which I think has captured the imagination of the general public as much as of professional mathematicians for more than 40 years now. And so in this talk, what I want to do is I'll begin by telling you what it is, although I imagine many of you know the definition. I'm imagining that a number of you have generated images of it yourself, played around with it on the computer. I want to say a little bit about why it's important to us as research mathematicians, and what we'd still like to know about it. It's still not fully understood, although we've been studying it for so many years. And with this talk, towards the end of the talk, I'm hoping to describe a little bit of what I'm doing in my current research projects, where the techniques are really coming from some other areas of mathematics, and specifically, as Ursula was mentioning, in arithmetic geometry or number theory, and how these other areas might shed new light on this very mysterious and wonderful and beautiful object. So first, what is it? So this is a set, a compact subset of the complex plane. There I've drawn for you the real and imaginary axes, so you can see where it is. To give you a sense of scale, I've put the number 1 and the number I on the slide. I is in the Mandelbrot set. The number 1 is not. Okay, so what is it? So each complex number C determines a particular sequence of complex numbers iteratively. The recursion is written there on the slide. You start with 0, and then iteratively you square your number and add C. And you repeat this process. This gives you some sequence of numbers. And the Mandelbrot set, I have a definition here. This sequence is called the orbit. The dynamical systems language for such a sequence is an orbit of the starting point. And then by definition, the Mandelbrot set is just this. It's just the set of parameters C for which the orbit of 0, under this very simple recursion process, is bounded, remains bounded. In fact, more concretely, one can say for which the orbit of 0 never gets bigger than 2 in absolute value. So it's a very concrete bound that one can give. Okay, so why is that interesting? Why have we spent so many years studying this object with this kind of peculiar definition? Well, the reason is because, the Mandelbrot set is so much more than just that, the set of parameters for which the orbit of 0 is bounded. I would say, one of the things that makes a mathematical object so interesting to mathematicians is that when it arises in many different ways, that different ways of studying something bring you right back to the same object. Even surprising definitions that turn out to be the same exact thing. This is one of those objects. There are actually lots of different ways to arise at the exact same thing. I've hinted a little bit at this in the next slide. I won't give you all the definitions. There are very few words on this slide, but I won't give you all the definitions. But just to suggest why this is a little bit interesting. So even within the study of this particular family of degree 2 polynomial recursion, so I've written the recursion down here, but really this is studying a family of discrete dynamical systems defined by a particular degree 2 polynomial, z squared plus a constant. So even within this particular family, there are a number of ways to define the Mandelbrot set in terms of the dynamics of this map F. So it's the set of parameters for which the Julia set, or the chaotic locus for this dynamical system, is connected. It turns out to be, the boundary of this set turns out to be what we call a bifurcation locus for this family. It plays a very important role. More than that, actually, its shape, its topology is really governing global features of these dynamical systems in a way that I don't have time to talk about today. I like to think of it myself as what I've called here a street map for this family of quadratic polynomials. Each region of the Mandelbrot set, each part of the Mandelbrot set has what we call an address, a combinatorial address, which you think of as like an address. Where are you, or how do you get to someplace, and describes the various combinatorial features of the different dynamical systems that arise just from iterating this very simple family of dynamical systems, or I should say seemingly simple family of dynamical systems. But beyond these quadratic polynomials, it's also something I would call universal, because this same image, this same bifurcation set arises when we study a lot of different nonlinear dynamical systems. And I'll say a little bit more about this in a moment. But let me go back in time and say a bit of the history of this set. I love this image. This is the first published image of the Mandelbrot set from 1979. Or maybe it was only circulated as a preprint in 1979, perhaps appeared in print in 1980, of Brooks and Metelsky. Although right around the same time, Mandelbrot himself was also studying this object and started to produce images of a little bit better quality than this particular image. And this is what made it popular. Wow, it was just this amazing looking thing. What is it? Why does it look like that? And one of the first mathematical results about the Mandelbrot set, which is a very simple statement, and very simple to prove now. I will show you the proof in one moment, or sketch it for you. But anyways, it's just that the Mandelbrot set is connected, which I should say was not at all obvious. Certainly at the time, with my computer, I just for fun, I don't know if I hope you can see the dots all around the Mandelbrot set. So with my computer, I set it to produce an image with low resolution, and you can see that you get this picture that's, Mandelbrot, a piece of the Mandelbrot set with lots and lots of dust around it. So it's very hard to say, like, why would people even think that it was connected when you see all this scattered dust? Here's another image, by the way, from just a few years after that first image. This one is not one of his first, but this one was published in 1983 in an article of Mandelbrot. He called it the M set at the time. And then later, mathematicians refer to it as the Mandelbrot set. Anyways, so that was, of course, much better image than this low-resolution picture that I've produced, but you still see these little specks of black. Again, it's not obvious that it was connected, but I want to say, actually, that the disconnectedness, in terms of how it looks, is not an artifact of computer graphics, or just setting my computer to have low resolution. Even if you increase the resolution and you have a lot of computing power, your set will still look disconnected. At least if you draw it this way, just in a black and white or a black and pink picture. What you see, however, when you increase the resolution, I don't know if you can see that from where you're sitting, but those specks of dust are, have shape. Each of them is a little copy of the Mandelbrot set itself. So the specks resolve themselves into little Mandelbrot sets, but it still looks very disconnected. This is one of the reasons that you see such beautiful pictures, I should say, of the Mandelbrot set. Oh, wrong way. Such beautiful pictures of the Mandelbrot set is because we don't use a simple yes-no algorithm to draw the picture. We use a mildly more sophisticated algorithm, what we refer to as escape time algorithm, which just means I'm checking for a given pixel, for a given parameter c, I'm checking if the orbit escapes, if it gets big under iteration. How about we color the pixel according to how long it takes for that orbit to get large, to get bigger than 2 or bigger than 10. You can iterate however many times you want, and you get all sorts of beautiful pictures and beautiful colors. And so those colors are the colorful pictures are spectacular to look at, but they're also mathematically meaningful. And one sees how the structure of the Mandelbrot set really comes out as soon as you add all the beautiful colors. You see that those specks, those little mini Mandelbrot specks, are actually connected to this main body, what we call the main molecule of the Mandelbrot set itself. And you start to see all the extra structure, the decorations, everything that's actually a very, very intricate set. And many mathematicians have spent many, many years exploring the details of this set. I said I would sketch the proof. I just wanted to mention one idea. I didn't even actually. This is not really a sketch. This is just an idea. In this case, to prove that it was connected, the idea was just to observe. This family of polynomials. They're polynomials. This is a holomorphic function in Z. Indeed, it's polynomial, and also in the parameter C. And one can construct iteratively a conformal map, or the Riemann map, from the complement of the Mandelbrot set to a disk. And one can do it essentially explicitly. You write down, you take iterates evaluated at 0, and you show that some limit exists, and you get a conformal map. So the proof is really just a couple lines long. Anyways, that I thought was the first sort of important mathematical theorem about the Mandelbrot set. And the second, which is actually not just one theorem, but many, many theorems over many, many years and by many, many people, is that the Mandelbrot set is universal. And I've mentioned some of the early names, but I also picked out McMullen from 2000 because it was his paper that is entitled "The Mandelbrot Set is Universal," so of course I wanted to give him some credit for that. Universal, so what does that really mean? So this was the idea that explains the little copies of the Mandelbrot set. Why do we see everywhere dense in the boundary of the Mandelbrot set? Why do we see little Mandelbrots? It's what we call a renormalization theory. Renormalization came up earlier this morning in the talk, in the second talk this morning. Stefan, is that his name? I don't know him personally. So, but in any case, the concept of renormalization came up earlier today, and this is something that comes up in physics. It comes up in a lot of different areas of mathematics, and we have our own renormalization theory, which describes these families of dynamical systems. You have this family. Of course, they're quadratic polynomials by definition, but if you take a very, very high iterate of the polynomial, in other words, a large time scale, a very, very high iterate, and a very small geometric scale at a very small level, it behaves like some quadratic polynomial, some possibly different quadratic polynomial. So you're shrinking the space, extending time, and you get some version of renormalization that explains all of these small copies. But it's not just small copies within the Mandelbrot set itself. This universality I mentioned extends well beyond the family of quadratic polynomials. It appears in other families. I just want to mention two examples. Newton's method, if you recall from calculus class, and we teach Newton's method as an iterative process for finding roots of polynomials. Remember, you start with an initial guess and that you hope is close enough to the actual root, and then there is some iterative process involving the derivative of your function that converges, in fact, very fast converges to the root of the polynomial as long as you start close enough. But it was known that if you take, say, a degree 3 polynomial and you try to find its roots in this way, maybe you make an initial bad guess. Your guess will not actually your iterative process will not necessarily converge to one of the 3 roots of your cubic polynomial. It might get tangled up in some other attractor, might get lost and not find one of the 3 roots. And if you plot a parameter space of cubic polynomials and you start with, you make some initial guesses and you track to see where it ends up, you find in your parameter space pictures copies of the Mandelbrot set. And this, when I first learned about that when I was a student, that was really eye-opening for me. What on earth is this little Mandelbrot set creature doing in this space of cubic polynomials when we're studying? So the iteration for Newton's method, I say for cubic polynomials, it's the iteration then of a particular degree 3 rational function, is if you work out the formula for Newton's method, if you remember it. Anyhow, and then it just shows up over and over again in these bifurcation diagrams and parameter space pictures associated to many, many families of dynamical systems. For fun, I put these 2 slides. This was an example. I didn't even write down the formulas, but this was some other family of maps that I was studying in a project just a few years ago. This was an image of its bifurcation locus, where certain bifurcations are taking place. This has some Mandelbrot-like features, but it's not itself a copy of the Mandelbrot set. But by this universality, I knew that those Mandelbrot sets had to be there. They have to be there. In fact, really everywhere dense in my bifurcation locus, I should be finding Mandelbrot sets. And in this particular example, it was one of the hardest to actually find them. So for fun, I really went searching everywhere in this black region until I finally found one. Turns out if you zoom in by a factor of 10,000, you get, can you see it? You get this very distorted baby Mandelbrot set. And those appear everywhere, all around in this set. So sometimes they're hard to find, but they will be there, at least in these classes of systems. These are analytic families, functions of an analytic parameter. The functions themselves are analytic, and there is a single critical point, just as for quadratic polynomials. So there are some hypotheses that have to be satisfied in order to see the Mandelbrot set, but they're relatively simple conditions. So that was universality. How am I doing on time? Okay, so the fundamental question, or one of the key things that we'd still like to know after studying this set for more than 40 years, there's really this fundamental question we have, which is, I said that actually we have a good combinatorial understanding of the set and how all the pieces of it, I should say, it's connected, but if you look at, say, the interior components, how all those pieces should fit together, one with the other, and we have a very, very good combinatorial understanding of it, modulo some very important question, which is here on this slide. So I formulated it roughly at the top here. Can we give a complete topological description of the Mandelbrot set? And one of the ways to make that precise is a conjecture that really dates back to the work of Fatou more than 100 years ago, and was, of course, revisited in the work of Douady and Hubbard in the 80s. I don't remember the year, so I just put approximately 1985, where they've conjectured that most of these dynamical systems, these quadratic polynomials, most in a topological sense, that is to say, a dense set of parameters, corresponds to what we call a hyperbolic dynamical system. And I don't want to spend time on the definition of hyperbolic because it's not important for this talk, but conceptually it means easy. Okay? Conceptually it means we understand it. Okay? Technically, it means there's expanding on the Julia set. There's a way to describe the map as expanding on its chaotic locus, some uniform expansion rate. But anyways, what we believe is that for a big, open, and dense set of parameters in this family, we can understand the dynamics, and we don't know if that's true. So a priori, there is some connected component, as it turns out, of the interior of the Mandelbrot set, which is perhaps what we call a ghost component that might not consist of hyperbolic dynamical systems. And we don't yet know how to rule that out. This is still something that's been bothering us for many, many years. Okay. So I consider this really a very fundamental question. And as I said, this is still open. This is something we'd still like to know. Now, there's been a lot of progress towards this problem. Not so specifically addressing this question, but there are lots and lots of related, interesting problems, other questions that would imply, other conjectures that would imply this if resolved, and there's been a lot of work on those other problems. You might have heard of what people in the field call MLC. The Mandelbrot set is locally connected. This is a big conjecture. If you could prove, again, the topological features, if you could prove this set is not just connected, but locally connected, that would imply this density of hyperbolicity conjecture. So there's been a lot of work in that direction, but it's just out of reach. So it seems, or maybe not. Maybe it's still really far away. Anyhow, there have been a lot of interesting mathematical developments. And so what I want to do, so maybe I should say, just to be clear, I am not solving this problem. I have not solved this problem. I wish I could be standing up here and announcing to all of you that I have a solution, and I do not. I would love to. But what I wanted to do with this talk is to go a little bit deeper into the Mandelbrot set and aspects of it, and especially some aspects that are connected to, number theory. I mentioned that earlier. To number theory or some arithmetic features, and to see if we can get any additional information from that. Okay. So on this next slide, I'm describing, there's a distinguished subset of the Mandelbrot set, which we consider very important. I'm calling this is some countable collection of special points. And what is a special point? A special point is one of these parameters C for which the orbit of 0 is finite. Okay, there's another name, but okay, remember, by definition, the Mandelbrot set is the set of parameters for which the orbit of 0 is bounded. And inside there, we have the set of parameters for which the orbit of 0 is finite, by which I mean, of course, it cycles maybe back to itself. So there's a discrete and countable collection of yellow dots in my picture that correspond to parameters where the orbit of 0 comes back to 0. So it cycles. And then there's another countable collection, which is in fact dense in the boundary of the Mandelbrot set, where the orbit of 0 eventually cycles. It doesn't come back to itself, but it might cycle somewhere else. All of these points, they're what we call post-critically finite, or PCF. They correspond to, post-critical. So 0 I didn't mention. What was special about 0? 0 is the unique critical point of this polynomial. It's exactly where the derivative vanishes. And from a more global dynamical point of view, it is very important that we're looking at the critical orbit as opposed to an arbitrary orbit. We could draw the same picture looking at the orbit of 1, but it wouldn't be so dynamically meaningful. It wouldn't be so important. 0 is very, very special because it's the critical point. So to say the orbit is finite, we have this language for it. We call it post-critically finite. So on my next few slides, I interchangeably say PCF for post-critically finite, or maybe I'll say special. But these are, I consider, very special points, these yellow dots. And they play a very important role in our understanding of these dynamical systems, mind you, both these and other families as well, because, again, this Mandelbrot set arises in lots and lots of different families. It has this universality feature. Here are a few examples of why these yellow dots are important. So these are some concepts that go back to the 80s. So for example, each of these interior components, these interior regions of the Mandelbrot set that you see, notice you'll see that it has a yellow dot in it. Every hyperbolic component, so the ones that correspond to those easy maps, what we call the hyperbolic ones, has a distinguished center, not necessarily the geometric center, but what we call a center. And that's one of these post-critically finite examples. And because the orbit is finite, it allows for us to encode the dynamics with a finite amount of data. And in fact, there's a complete combinatorial description of the associated polynomial dynamics, not just the orbit of 0, but I mean the orbit of every point, essentially every point, just in terms of what 0 does. So we get a lot of information about all of the dynamical systems in that family just by knowing what the center does. And we have ways to combinatorially classify all the different possibilities of all of these hyperbolic quadratic polynomials, especially via what we call Hubbard trees. This is one example. One type of combinatorial object that we can use. These yellow dots, I said that they are well, they're discrete in the interior of the Mandelbrot set, but they're everywhere dense on the boundary also. And in fact, they're not just topologically dense, they're uniformly distributed with respect to a very natural measure, a very natural distribution on the boundary of the Mandelbrot set, specifically what turns out to be the harmonic measure on the boundary, at least as seen from infinity. The same measure that you'd get if you were to run, say, a Brownian motion on the outside, starting at infinity on the outside of the Mandelbrot set, and determine the hitting probability of your Brownian motion. That's the same as this harmonic measure. And these points, these yellow dots, if you order them by orbit length, and say you look at all the yellow dots of orbit length n, and put equal weight on all of those, and let n go to infinity, they will become uniformly distributed with respect to that measure. And that measure is very important for us. It encodes some information about the bifurcations that take place in this family as you pass through the boundary. So these points also see this bifurcation data. So they're important from that point of view too. But I want to mention this. They also have this arithmetically special feature. Remember, I'm just looking at polynomials, quadratic polynomials. So these parameters C, these special parameters C, are just roots of some polynomial equations with integer coefficients viewed as a polynomial in the parameter C. You fix some iterate n, some iterate m, and if you want these two iterates to coincide, in other words, the orbit cycles, then the C is just the root of some integer polynomial, monic polynomial, making it an algebraic integer. So all of these C's happen to be algebraic integers. And we can then start using some arithmetic tools to try to analyze features of these special points. So for example, we could study properties of their heights. For example, their Weil heights. It turns out they form a set of bounded height. Height, if you don't know, is a measure of arithmetic complexity. I mean, one can talk about the height of an algebraic number. It's a way to measure, in some sense, how complicated it is. I won't go more into that. I just wanted to mention. So one can study various aspects of these heights. One can even build a height function on all of Q bar, which has very good properties from a number of different points of view. I won't go into that either, but there is a very nice height that lives on this entire space, on all of Q bar, which has exactly these postcritically finite points as the zeros, the minimal height points. They're minimal complexity with respect to some naturally dynamically defined height function. And we even have equidistribution of a stronger sort. It's not just if you take all of the special points of orbit length n, but maybe you just take a sequence of them and look at their Galois orbits. Those collections of orbits turn out to also be uniformly distributed, which is a stronger statement than looking at all of them. You can look at pieces of them, and they're still nicely spread out. And these are some results from the last, say, 2 decades. Okay, so, and I wanted to say, wow, and I've already used up nearly 30 minutes, but I wanted to also say, going back to this fundamental question, remember I said, so this main conjecture, we want to say that for a dense set of C values, in fact, we want to say for the entire interior of the Mandelbrot set, all of those polynomials are hyperbolic, and that's still open. That question can be formulated in terms of my special points, so I just want to mention, you can reformulate the conjecture in this, well, okay, yellow dot is not precise, but anyways, you could reformulate the conjecture as just saying that every connected component of the interior of the Mandelbrot set has one of my yellow dots. I said you can see a yellow dot, by the way. Remember, I said you can see them in each of the connected components of the interior that at the scale of the picture I've drawn. And if you zoom in anywhere, you would continue to see yellow dots. So everywhere we've looked, we've found yellow dots. But we cannot prove that every interior component actually has a yellow dot. And that's really what we'd like to know. And so we want to understand more about these yellow dots. Okay, so here are some fun things that we can do with yellow dots. I've been sort of playing around with And I say playing around because it really is kind of, it was just for entertainment. I just wanted to know, well, what kind of numbers are they? And are there relations between them that we might not expect? Like maybe I expect a dot that corresponds to, say, a cycle of period 4 to be related to another dot that corresponds to a cycle of period 4. Maybe they're both roots of the same irreducible equation over Z. But what other geometric or algebraic relations might there be between the different special points? So here's just concretely one example. Suppose you take some kind of real linear, a real line inside the complex plane, which I'm identifying with R2. So we know if we take any two of my special points, of course you can draw a line joining them, but maybe there are other dots on that same line. And if so, what would that mean? Is there some kind of dynamical relation between 3 dots on a line? Why would they ever be collinear? Can you find such triples or quadruples of points lying on a single line? So just to point out, of course, along the real axis, we already know that there are infinitely many of these yellow dots. There are infinitely many of these special points along the real axis, so that's a kind of special case. And I also happen to know that along the imaginary axis, there are also at least 3 special points. 0 is a special point, I is a special point, and minus I is a special point. So the imaginary axis happens to contain 3 special points. But I and minus I, they're symmetric by complex conjugation. Their dynamics are also symmetric, essentially, by complex conjugation. I mean, they're not unrelated. I mean, any vertical line through other dots will have its complex conjugate pair. It's just that this one happened to also go through 0. So maybe that was lucky. Maybe those are distinguished. I don't know. So let me say what was known. Just recently, a group of mathematicians I want to mention were exploring a similar question. They didn't formulate it this way, but this is a consequence of their main theorem. They observed that if you take any real algebraic curve, so I'm in R2 here, which I'm, as I said, identifying with C. If you take any real algebraic curve and you look at the special points along that curve, the only such curve that might have infinitely many special points is the real axis. Okay, so I'm taking any other real algebraic curve, unless it contains the real axis as a component or it is the real axis itself, there will only be finitely many of these special dots. So the real axis really and truly is special. Okay? Really and truly, the real subfamily does play some kind of special role. And how am I doing on time? Okay. Before I go on, I just want to remark already at this point. So I said this was really just for fun. I'm playing around with the points and the geometry and asking these questions. But this particular question that they were looking at was actually motivated by something. It wasn't out of the blue. It was motivated by some analogous results in the setting of families of elliptic curves. So what they actually proved, I haven't stated their theorem, was a similar statement, but looking at algebraic curves over C2, not in R2, and looking at pairs of special points that have both coordinates being special. And the theorem they proved, which was an exact sort of, in some sense, dictionary translation to a theorem of André and Edixhoven in a slightly different form, which was about algebraic curves in C2, where you identify C, in that case, with the family of elliptic curves via their J invariance. And they were looking at the algebraic curves that pass through infinitely many special points in that setting, where special in that setting is where both components corresponded to elliptic curves with complex multiplication. The answer in that case is that the curve can be a modular curve. There's, in fact, an infinite collection of exceptions in that case. And here we have only this one exception, which corresponds to the real axis in R, but would be the diagonal in C2, if you complexify the problem appropriately. So there was some external motivation for this question. By the way, the proofs the proof in this case is by necessity, actually, it turns out quite different than the proof in the setting of elliptic curves, but there are some parallels that I don't have time to talk about. But the motivation really came from somewhere else. So I've been exploring this. I have been working on similar problems, and I was wondering recently, okay, as I said, but how many special points can there be on those other curves? Maybe not infinitely many yellow dots on a given algebraic curve, but on a given line, can there be 3 dots as it appears there are in the picture that I just drew, or is it fewer? So this is something I've been playing around in joint work with Myrto Mavraki, who was a postdoc with me for the last few years, but she's now moved to the University of Toronto. And here on this slide, I've stated 2, I call them sample results. These are sort of instances of a more general result, but I think this one is, these special cases are perhaps a little easier to absorb at first glance. So let me just read example theorems for you. So for example, one thing we don't know, sorry, let me go back for 1 second. I said here, how many special points can there be on some given curve which is not the real axis? Okay, the real axis has infinitely many, but what if I'm just handed a curve? How many can there be? Okay, I don't know the answer to that. I'd love to know the answer. So if someone has some ideas of how to answer it always, I'd love to know. But what we can show, for example, is that there's a uniform bound on the number of those yellow dots on a curve that depends only on the degree. So for example, the statement is, for each degree d, corresponding to the degree of the algebraic curve I'm looking at, there is a uniform bound on the number of special points on any of these real algebraic curves of degree d. So there is some uniform bound, as long as I throw out the real axis as being a component of the curve. So there's a uniform bound, but I don't know how big that has to be. So even among lines, I don't actually know how big that has to be. But one thing we can say is that for a general curve of a given degree, which really means most curves from an algebrogeometric point of view, most curves in a given degree, we do know the bound, and it's sharp. We know that for a given degree d, a general algebraic curve, real algebraic, I'm doing real here, but it works for complex as well, a real algebraic curve will contain at most this many special points. Okay? So we do know what the bound is typically for a general such curve. And as I said, this bound is actually optimal. I mean, in the case of lines, this d equals 1, this is just the number 2. Of course, there are a lot of lines that have 2 yellow dots, because as I said, you can take any 2 yellow dots and you can join them by a line. This bound turns out to be optimal. So what's on the next slide? Oh yeah, I know what I was going to say. I wanted to say a little bit more about the degree equals 1 case. By the way, the space of all lines in R2, I mean, if you think of it just real geometry, there's a 2-dimensional family. You have the slope and the y-intercept that you can vary freely. So this is a 2-dimensional family of lines. So a general would just mean, well, outside of maybe some 1-parameter families of lines. But actually, we can do better. In practice, we can actually do quite a bit better than just studying the general algebraic curve in degree d. In fact, we can completely classify all of the exceptional positive dimensional families. But in every case, there might be a finite smattering of examples that we cannot control. So for example, for lines, we can say, well, outside of finitely many lines, we know that there will be at most 2 of these special points. And remember, I showed you 2 of those exceptions. Those exceptions do exist. Remember, the real axis is an exception. It is a line with infinitely many special points. And the imaginary axis is a line with at least 3 special points. But how many points are there on the imaginary axis? I don't know. I'd love to know. If anyone has a proof, I'd like to hear it. How many lines are exceptions? What are the other exceptions? besides the real and imaginary axis? I don't know. Maybe there are no other exceptions. I'd love to know it. I think it's really fun, and I'd like to know the answer. And I don't know how to handle the exceptional cases. Okay, so what kind of math are we actually doing? So what's really going on? What is this an instance of? Well, I hinted at it on the previous slide in the theorem of Gioka, Krieger, Nguyen, and Ye. The connections with the study of elliptic curves, or more generally, the connection with the study of abelian varieties. Let me just say what the strategy is, and then I'll say a bit more of the background. So this is very vague. I am not going into any details at all, but conceptually, what do? We start with, actually, first of all, we start by working over the field of complex numbers. It's just a lot easier to work with an algebraically closed field. We work over C. So we take those real curves and we think of them as curves over C. We work in C2. In any case, so let's just say we start with some algebraic family of algebraic curves in some degree. So X here is my parameter space of curves. Maybe it's the Chow variety of all curves of a given degree D. And curly C represents a family of algebraic curves. And I want to assume that my family is algebraic, is defined over Q bar, because the methods I want to use are going to be algebraic. You can always take your family and put it inside one that's defined over a number field if you wish. So it's really no loss of generality for the types of statements I was trying to prove. So let's say we have a family of curves, and what do? So then we start doing some arithmetic geometry. We build a certain line bundle on our big space, on our space of curves, and we want to construct a height function. We want to measure arithmetic complexity of the points. Because remember, I told you earlier that there was already a naturally defined height function on this space of polynomials, at least the ones defined over Q bar. On that space of polynomials, there was some naturally defined height function for which the special points were minimal complexity, 0 height. And so we wanted to build a similar function, but maybe now not on just this copy of C or Q bar, but on this big family of curves. In fact, it's convenient to not just work on this family of curves over this parameter space X, but a particularly large fiber power of this family of curves. It turns out, depending on the dimension of your space of curves, you have to take a fiber power which exceeds the dimension. So there are technical reasons for that, and geometric reasons for that too, that I don't have time to talk about. But there's this construction that was not our invention, that we're mimicking from another setting in order to do this. And then we build a height function, which again means defining a certain line bundle on your space and defining a metric on that line bundle that has good properties, doing that over the field of complex numbers, and repeating the same construction at the other places of the number field over which we're working. So we do it p-adically for every prime. Primes came up in Akshay's talk. I'm not going to say anything more about working over primes of number fields. But so the idea is that you build the geometry, the complex geometry on one hand and p-adic geometry on the other side. And you do this in order to build these height functions, and you want to say, these are good height functions. So to wrap up the argument of the proof, the key analytic step, then, is to say, if you had too many special points on your curves, for example, a family of lines with 3 points on them instead of 2, not even a whole family, an infinite collection, some infinite sequence of lines that all had 3 points on them. That's too many. And if you have that, you can build into this family, you can force from this family, look here, a non-trivial self-similarity of the Mandelbrot set. A non-trivial self-similarity of the Mandelbrot set. Remember, I said that these special points were equidistributed, uniformly distributed with respect to a natural measure on the boundary of the Mandelbrot set. And not just when you take all of them, when you just take some of them and you look at their Galois orbits. So they, together with their Galois conjugates, are uniformly distributed. We work over a number field, we take the Galois orbit over that base number field, and we get lots and lots of points, not just the ones we found, but maybe many, many more, enough to become dense on the boundary of the Mandelbrot set. And if you had 3 points on the lines, it would force some kind of non-trivial symmetry. It could, and it does, force some kind of non-trivial symmetry between one side of the Mandelbrot set and the other. But there are no non-trivial symmetries of the Mandelbrot set. There are no non-trivial symmetries of the Mandelbrot set. I see I'm out of time. So there are 2 things I want to mention just before I wrap up. What am I talking about? There are no symmetries, and again, where did the ideas come from? So just very briefly, you don't have to read all this, I just wanted to say, this strategy is not new. It's only new in this setting of bringing the ideas to the context of the Mandelbrot set. The strategy is really inspired by many, many years of theorems and results and questions, conjectures about abelian varieties and families of abelian varieties, and as I said, elliptic curves and those with complex multiplication, and the number theory and the Diophantine geometry of those objects and those families. And so we've taken the ideas from that setting. I just want to mention that some of the methods that we've been using over these past few years do go back the other way. We are able to take some of our complex dynamical methods and push them back across that bridge and say, hey, we can actually give some new proofs in the setting of, in the other side, in the group setting. But anyways, I just wanted to emphasize the Mandelbrot set today. And so, of course, there are many names that I've just thrown. These aren't even all the names. I mentioned one reference here. I'm happy to talk more about the details and the references with any of you if you're interested after the talk. The last thing I wanted to mention was just to clarify this claim that I said. At the end of the day, we reduce the entire thing via arithmetic geometry and this arithmetic intersection theory. So we're proving that some line bundle has a top self-intersection number positive. We need to prove a positivity. And at the end of the day, we reduce it to to observing that the Mandelbrot set has no conformal, or algebraic in our setting, but anyway, certainly no conformal self-similarities, which was really only formalized very recently by Yusheng Luo as one of the results he proved in his thesis just a few years ago. Well, he finished a few years before this, but it was published in 2021. So Yusheng Luo gave a nice proof that shows that the Mandelbrot set has no conformal self-similarities, which might surprise you. Remember, I said that it is sort of self-similar. I said there are copies of the Mandelbrot set everywhere in its boundary. But none of these are little conformal copies of the Mandelbrot set. They're quasi-conformal copies of the Mandelbrot set. So they're better than just homeomorphic copies. There is some kind of rigidity, but it's not conformal. I mean, so informally, what I mean by the conformal similarity is if you take a little open set here and you map it, say, conformally, holomorphically, analytically, to some open set over here in such a way that you take the boundary of the Mandelbrot set to the boundary of the Mandelbrot set, you can't. I mean, it would not align. So the only way to do that is by the identity function, or if you allow orientation reversing, by complex conjugation. So I think maybe I should just stop here. So thank you.